First off, read in your packages. Next, we're going to split our data so that way we can look over the possible values for our hyperparameters. It's called a hyperparameter search. So here we're going to read in the iris data set and split our data so that way 70% is for building our models and then 30% is a validation data set to determine which hyperparameters are optimal. Here we're just creating a index or a column of true or false values to then split our data. So that way we're using every row and just assigning approximately 70% to our train and 30% to our validation. There are packages out there specifically for data splitting, but this was just a quick and dirty way to give an example. Next, we're going to actually try to build our first LOESS. So here we're using the LOESS function. We're specifying our formula, so this is similar to any other modeling technique where you specify your target, tilde, and then separate your predictor variables of interest. Here we're just saying period, which means use all other columns in the dataset other than petal width. We're doing this on our dataset we just created called train, and 30% span, degree of 1. And if we do this, we get an error, and that's because we have a categorical variable in the dataset. If it is a variable you want to use, you're going to have to find a way to convert it into some numerical form or do multi-staging in your modeling, but unfortunately LOESS is not a method that's going to be able to use these categorical variables as is. So for this example, we're just going to ignore that categorical variable and focus on all these numeric variables. So if we try again, here we see we don't get an error and we can actually print out our resulting model and we have a successful model fit. So yay! So thing one is no categorical variables. Next is normalization. Now the tricky thing about normalization is you're not going to get errors for this, so this is really important. You understand that you most likely need to do this. There are very rare situations where you don't want to normalize. So that's just saying, you know, if you had two variables, salary and height, salary, there's a lot more variation there, and so when you calculate your local neighborhoods to build your localized models, it's going to be purely determined on salary because there's swings of $5,000 and $10,000, whereas your height is differing by units of 1. So normalization is just saying, hey, I want to get everything on a similar scale. Now the thing I wanted to bring attention to is just that LOESS has built-in normalization. You can just set this equal to true and it handles it for you. The downside, potentially, I'm not sure if it's a downside, is that they do this like weird trimming, so I don't know exactly what this is, but I'm guessing it's looking at the like 10th and 90th or 5th and 95th percentile, and then based off of those ranges doing some standardization. What I have here is another option. If you want to know exactly what's going on underneath the hood, you can instead set normalize to false and then just normalize the data on your own ahead of time. In this case, maybe I just want mean 0, variance 1, and that's it. Keep it simple. And I have some code here to walk through if you're interested. But for the purpose of this walkthrough, we're just going to say, okay, let's use the built-in normalization capability. So that's number 2, normalize your data to make sure that all variables are getting a fair say in how to define local neighborhoods. Next is a large enough span. So one error you might see when you're using the LOESS function is a lot of this printout. And all this is saying is that your span is so small that, let's say you had 100 observations and you set your span to 0.005, that would mean you only get half an observation. So obviously that isn't enough data. You also can run into issues even if you have a whole observation. If you have like a degree equals 2 model, there's too many terms you have to fit to too small a subset of data. So just when you see these error outputs, just know you should probably increase your span. So now we can jump into actually trying to fit and determine the exact LOESS model we want for our data. So first off, you're going to want to have a metric of interest. So this really can be anything. One of the most common things used is root mean squared error, but by no means does it have to be. It really can be any function you want. Here we're saying I care about minimizing the root mean squared error. So we're going to try a bunch of different spans and degrees, and then look at the training and validation root mean squared error. So looping over both, we're going to fit our model, and we do want to normalize, and we're going to do that span in that degree. The one thing I did change, or I guess add, is this control equals surface direct. You can either direct or interpolate are the two options here, and direct ensures that you're going to get fitted predictions on a validation data set. Interpolate, I think, is like computationally faster. It produces slightly different results, but you can run into issues when you try to predict outside the bounds of your trained data set, which actually happens even in this small example. So I prefer to use direct, and direct is what I walk through in my other LOESS video, which I'll leave a link to in the top right corner of the video. So here we have 1%, and it's extremely squiggly because it's only looking at the nearest data. At 6%, it's very closely mapping to the actual true pattern. And then once we get to those higher values, you see it's actually starting to over smooth. So when I'm walking through that video, I'm talking about the direct method. Interpolate's a bit more complicated, and I don't fully understand it, but it's doing some type of smoothing, I think. But anyways, so that's the one thing I added here. And then finally, we're just going to record that train invalid root mean squared error, looking at both of those. And this is where we use the predict function on our model that we just built. So we're building this model, it's getting updated, and then we use the predict function to get our predictions for the validation data set. And then finally, we're just appending those results. So looping all over those results, we're going to get them all, and then best, we're going to just say, hey, of all those root mean squared errors for the validation data set, which one is the minimum, and then return that index. So let's go ahead and run all of this. And those warnings, if we want to print them out, this is the issue we talked about before with the span being too small. So here we're looping over things, and so I don't really care that some of the times it's really bad fits, because that should carry through in the validation performance metrics. If we have a final model and we get these errors, that's going to be concerning. The hyperparameter search, we're okay with this. So now if we want to look at the results data set, or let me do that. So just to show you what the structure is, and then best is just pulling our best model. So here we see the very best model we have has a span of 25% and degree of 0. And that validation root mean squared error is 0.32. Now, a couple things. Ideally, your train error metric and your validation error metric are going to be a bit more similar. This looks like extreme overfitting, but really we're just running into issues with a really small data set. I think is the main issue. But the good news is this is on the validation data set, and this is the best performing one. But this would be a bit alarming in modeling to see this large of a disparity between your train and validation typically. Now I also have a pretty simple plot here if we want to take a look. So this is just a heat map of those two hyperparameters. So degree can be 0, 1, or 2, and then span is ranging from about 0.1 to 1. And here we see that the best performance occurs when we selected that span of 0.25 and a degree of 0. So that is how you go about doing a hyperparameter search. Really simply, just do a loop and record your metric of interest, and then you can refit that model at the end. So here we're going to say I want to copy and paste that code from before. But instead of any old span, I'm going to take that best span that we just determined, and we're going to refit that model. And so that's what we're doing here. And that is how you fit a LOESS in R. For less code and more theory, check out my other video on the LOESS method.